All right, anything you want to bring up before we start going on today? Let me just make sure we still have the 6 people here. No more. Yep, we do. Okay, where we left off last time, we're in Chapter 5, Integration, Section 5.7, Natural Logarithmic Functions, Integration. And here are the guidelines that are trying to summarize just about everything we've done with integration so far. First, learn a basic list of integration formulas. Okay, I like to say it this way: use them enough they get to be your first cousins. You don't have to sit and memorize them or something like that. You know them. Okay, get familiar with them. Okay, number 2, find an integration formula that resembles all or part of the integral, and this is trial and error, and it's fine to make mistakes. Okay, just see if you can catch them. Find the choice of u that will make the integrand conform to the formula that you're trying to go for. When you cannot find the u substitution that works, try altering the integrand to see if something else might do. You might try trig identity, multiplication or division by the same quantity, addition or subtraction of the same quantity, long division. Says be creative. Sort of need to know where you're heading to know how to create, but try a few things. Even an error may give you insight into something that might work. Okay, if you have access to computer software that will find antiderivatives symbolically, use it. Okay, if you got that, check your result by differentiating to obtain the original integrand. Now, they left off the most obvious thing, especially from a calculus book. Go to a table. Most calculus books have tables, either in the front, the back, sometimes both places, and see if you recognize the form there. And again, that's going to hear something that resembles something that you're trying to get to. That's the key. So I don't want to beat this one into the ground. Any questions, or we'll move on? Okay. I thought we would move on. For some reason, you have to click on the screen before you'll move on. Okay, here's example 7. Solve this differential equation. Okay, now I think this is time for the whiteboard, sadly speaking. By the way, I think my wife's heard me gripe enough about writing with my right finger that I brought it up in a department meeting we had last week, and one of the other instructors has found a Wacom add-on that you can do, and that's basically an ionizing pen type situation. So my wife has ordered it. We're going to get it in, see if it works. So maybe the second half of the term I'll actually be using a stylus rather than my finger, and that I promise will go a lot better, because then I'll use my left hand, which I'm better at writing. So let's go to the whiteboard, and let me get this taskbar out of the way and also move the whiteboard. Whoa, goodness, I didn't know it would do that. Well, we just filled the screen with the whiteboard. All right, here is the problem we've got written in slow, agonizing terms. One thing about this microphone, it hangs against my arm, and that's irritating, but we'll live with it. Okay, dy dx pretty ugly d there. Dy dx is equal to 1 over x log x. Now, I don't know why they write this as a differential equation and then say solve it. Why don't they just write it as an integration problem and say solve it? Same thing, because the first thing you're going to do is wipe out the dx on this. In other words, write it in differential form and write the dx over here. And here's why we did that. we're trying to get all the x's on one side together, all the y's, and that's the only y you have is that dy, and then you integrate both sides. Okay, now nothing to pull out because the x and the log x is in both of them. That's what you're using as your variable of integration. Now, I can do the left-hand side. That's just going to be y, okay? Now, you don't have to do a c for both sides, so let's just leave off the c for now. The question comes, what do we do with the right-hand side? Anyone got an idea right now? An observation? Okay, well, let me start with my typical question. What's the most complicated part of that integrand? And before you say, and actually, if you were to say the log x in the denominator, you really are sort of right, okay? But I would say the entire denominator, because all your x's are down there. You don't have any in the numerator, which is where we usually like to do things. Now, what's the innermost part of the most complicated part of that integrand? Well, again, the innermost part here, I think you would have to say, is the log x, okay? So let's let that be our u, okay? You okay with that? Let u equal log x. See, you really need to be answering my questions and you come up with something and we'll try it. That's supposed to be an e there, and it's an awfully ugly e. Let u equal log x. And does anyone see why that's a really nice choice? Because what's your next statement? Anytime you have a let, follow it with a then. Or most of the time I'll say it that way. Then, it's a little bit better e, but not much. Then, of course, the next step is du. And what in the world is the derivative? That's the derivative of u. What's the derivative or the differential of u? What's the differential of log x? Somebody tell me. 1 over x dx. In differential form, you need that. Perfect. 1 over x dx. Okay? Now, take a step back and look and see if this has helped you any. Sure enough, it has. There's the 1 over x dx right there. That's your du. And here is your u, log x. So what you have here is the integral, because we don't have variables here, limits here, or the ranges here. This is a definite integral, okay? So what we have, the 1 over x dx is du, and the log x is u. So it's du over u, which is sort of interesting too, because what's the antiderivative of du over u? Help me, somebody. Oh, wait a minute. Here comes somebody, but they blocked the name so I can't see. I think it's Jesus. Okay, let me get Jesus here. There we go. All right. That should be up to 7. Yeah. All right. So anyone want to answer the last question? What is the antiderivative of du over u? You're going to think this whole problem is full of them. It's a log jam. That is the log of u. Okay? And you can do a plus c now if you'd like. I'm real tempted to make it a plus log c. That's the constant just as good as any. And by the way, this u should always be in absolute value bars because we have no idea what the limits are for the u here. So put it absolute value bar. And I think for right now I'm going to put log c. If that doesn't work out, I'll go back and change it just to c. And I can't write worth a toot here. Okay, let me see if I can get that better. Okay. Okay, let's see if I can get it this time. If I don't lift my finger in time, it draws. We'll just call that log c. You don't have to. You could just call it c. You can call it anything you want to. Just make sure you understand it's a constant. Okay. Now, what we do at this stage is plug in what u is, or u are, and that's log x. So this is the log of, believe it or not, absolute value of log of x plus, oh, let me see how they did it. No, they just put a c at the end. So rather than doing log c, they just put c. It didn't really gain us anything to put the log c there. Some problems it will, this one it doesn't. So we'll just leave it as a plus c. And that is indeed your solution. Y is equal to log of x plus c. Okay. And you could always go back and take a derivative of that. Dy dx would be 1 over log x times chain rule 1 over x. And sure enough, that's what you get here. 1 over x log x. Perfect. All right. Any questions on that? Okay. If not, we move to the next, oh, wait, sorry. I can get the cursor to show back up here. Let's go back to our PowerPoint 5.7 and go back to current slide. And that was our problem there. The solution can be written as the indefinite integral, and that's what we did. Why didn't they just give us that as the problem? It wasn't a differential equations course. You basically write this in differential form. Dy is equal 1 over x log x dx, and then integrate both sides. The integral of dy is y, and then you have the integral of that. Okay? Because the integrand, and I'll have to wait till this fades out, is a quotient whose denominator is raised to the first power, you should try the log rule. That's their little statement. I don't know if that is particularly helpful to you, but it may be, and if so, go for it. I look at this, my usual method, and say, what's the most complicated part? The denominator. Okay, what's the innermost part of that denominator? Well, the log x is most sort of the complicated part of that denominator, and derivative of log x is 1 over x, which is exactly what you've got there. So that's a perfect fit for u. Okay, there are 3 basic choices for u. One would be u equal x, one would be u equal x log x, and one, the one that we chose was just log x. Okay, now the first 2 of those fail to meet the u prime over u form for the log rule. If that's how you think of it, fine, go for it. The better way in my mind to think of it is if you choose log x as your u, the derivative of log x is 1 over x, and that's exactly what you got there. Okay, which is doing the same thing, but it seems like they want you to look in the crystal ball, see what the answer is, and then say, well, here's how you got the answer. Whatever floats your boat. Okay, third choice does fit. Let u equal log x produces u prime equal 1 over x log dx, I would have said, but u prime has a dx in it, and you obtain the following. Okay. Oops, here comes somebody, and I can't see who it is. I think it may be Jemanuel. Let me see if when I admit, nope, I couldn't see. Could anyone tell who that was trying to come in? The black box blocked it. I think it was Jemanuel.
It's Jay Fulham.
Oh, okay. Oh yeah, Jemanuel Pullum. That's it. That's who I thought it was. Thank you. It's sort of crazy that Zoom or whoever it is does is blocks it from my view, and you can see it better than I can. That whoever designed this didn't teach a class, I don't think. All right, thank you. So I think Jemanuel is here, or getting here anyway. That should give us up to 8 students. Let's make sure that's right. 1, 2, 3, 4, 5, 6, 7, 8. Got it. Okay. All right. So we've identified this. I don't know if it makes more sense for you to put the 1 over x in the numerator. If so, fine, do it, But they said divide the numerator and the denominator by x. Okay, whoops, and here's Anita. Good deal. Now that time it didn't block her. Okay, I could see her. So here's Anita coming in. This cord really gets in the way of my roll book because I keep it on my left. Okay. You can think of it that way. Divide the numerator and denominator by x. This would be a 1 over x up here, and this x goes out down here. If that helps you see it better, by all means do it. If you can see it just perfectly fine, that the derivative of log x was 1 over x, you saw it there, dx, seems like that's perfectly fine too. Okay? And now it won't advance until I click on the slide again. It's so bizarre. Okay. All right. And that gives you, if you do substitution, see, it seems like to me you ought to write this line first and then do this line. Your substitution would be let u equal log x, because that's the part in the most complicated part here, and your du would be 1 over x dx. Okay? So that would be your numerator then. So rather than keeping dx's here, which you're not going to keep, you're going to go to u anyway. And now no, they don't. They went straight to this is the log of absolute value of u. Now, if that makes more sense to you, do it. Go for it. Seems like the way, to me, of course, the way I like to do it makes more sense to me. Okay? But then you still have to, because your original problem was in x's, this is in u's, go back and substitute your log u in for log x in for u. And that gives you log of absolute value log x plus c. Now, do you still need the absolute value bars there? Yes, log x can be negative. You can't take the log of a negative number, but the log of a number can be negative. If you think about how the log function looks, anything between 0 and 1, the log of that is a negative number, because the log of 1 is 0, and then the log of anything beyond 1 is positive. But anything between 0 and 1, the log is negative. So yes, if this x had a value between 0 and 1, that's going to be a negative value here. You have to have the absolute value bars to take a log. Okay. Whoops, here comes somebody else, and I think this is iPhone. And if that's the case, I'm guessing James. Is it James? James Mullins? Yes. Who is it? Good, good. I thought so. I thought that's who you usually indicated when you came in. Welcome. I got your mark. Okay. Now, we're just finishing example 7, bottom of page 359. This is in chapter 5, integration, 5.7, natural logarithmic function integration. Okay. And we've already done it, but I was just showing you how the book did it. They substituted in, and that's your answer. And now it won't advance. Okay, until I hit this again. Oh, so the solution is y is equal to log of log x plus c, which is what we got. So, moving on. Any questions on that before we leave it? All right. Now we're moving on to integrals of trigonometric functions. Okay. Now, of course, this is going to require you to remember what the number one, what your trig identities are. Number two, what the rules for integrating some of the trig functions are. Some of them are a pain in the neck. Others of them are a lot easier to deal with. But you have to be able to recall those. So here's the first problem. Find the antiderivative, the integral of tangent x dx. All right, I guess it's time for the good old whiteboard again. That said, okay, I'm going to go on and clear the screen, and for some reason it's got a big box there, but the box is fading out. That's okay. All right, the integral of tangent x dx. Antiderivative of tangent x dx. Okay. Now, first you ask yourself, is there a function whose derivative is tangent x? If there is, we got it knocked. And the answer is no, there's not. Derivative of sine is cosine. Derivative of cosine is minus sine. Derivative of tangent is secant squared. Derivative of cotangent is minus cosecant squared. Derivative of secant is tangent x secant x. And derivative of cotangent is minus cotangent x cosecant x. No, there are no derivatives of any of your trig function that comes out being a tangent x alone. So, turn to your trig identities. Okay? Now, what's the simplest trig identity you can remember involving tangent x? Anyone recall? What is tangent x? I always, if I can't think of anything else, get everything in terms of sines and cosines. So what is tangent x in terms of sine and cosine? Either y'all need to talk with your trig teachers or you're very silent. Okay? Tangent is sine over cosine. I know y'all know that. Often called the ratio identity, sometimes called the quotient identity. It's just one of your main identities. Tangent x is sine x over cosine x. And that's a pretty ugly x. My finger kind of sticks on the pad sometimes and just takes off. What do we do with that? Does that make it any better? It actually looks more complicated to me. Hold on just a moment. It's getting a little stuffy in here. It's fairly warm outside today. So let me turn on my ceiling fan. Okay. So my typical question here is, what's the most complicated part of this integrand? Well, in general, numerators are fairly straightforward. Denominators are a problem. So let's let that be our u substitution. Let, that's a little bit better E than the last couple were, u equal that denominator, cosine x. Okay, and then what's your next statement always? If you have a let statement, you usually follows it by a then statement. And the then is usually your derivative. If u is cosine x, what is the derivative of u? Anyone want to tell me? I just said it a few minutes ago. What's the derivative of cosine? Minus sine. I must tell you this too. I went to make out your test. It was either sometime Thursday or Friday. I think it must have been Friday morning. And the test bank used to be fairly easily navigable, but now they're doing everything in PDF, not Word. No, I'm sorry. I had the option for Word. So yeah, I had the Word, but Word, rather than having an equation editor that makes sense, they just have a few little things you can do on an equation editor, and the rest of it, guess what you have to do? You draw with your finger. So here I had been struggling with this all week, I mean, ever since we've been doing writing on this, and there I had to do my integrals and things like this that they didn't have symbols for. I had to do them with my finger, and they did some really weird translations, but I think I finally got them all right. Okay, so what do we have here then? Well, here's a du is minus sine dx. Well, here we have a sine x dx. Well, we don't need the minus sign there, so let's multiply and divide everything by minus 1. Well, let's just divide everything by minus 1. So that gives us a minus du, which is just minus du, is equal to sine x dx, because this goes away and that's just sine x dx. So what we have then with the u substitution is sine x dx is minus du, so that's going to be the du here, and the minus way out in front here, and then we'll have the integral of, guess what, du sine x dx over u. So I'm just going to write it as 1 over u because I left the room for it, 1 over u du, because cosine x was uu, and minus sine x was your du, or sine x dx is your minus du. So we put the minus sign out here. So what does this give us? Please, somebody can do that one, can't you? Antiderivative of 1 over u du? Minus log u, that's supposed to be a u, the handle didn't come down, there it is, okay, plus c, and this time I don't think there's any advantage in doing trying to get fancy with the constant, just leave it like this. But because the original problem was in terms of x, let's put the answer in terms of x. That's a minus equal to the minus the log of absolute value cosine x. Because u was equal to cosine x. Now, and then plus c. Now, I assume somebody might say, do you really need the absolute value bars? Well, it depends on your domain for x. If the domain for x is between 0 and pi halves, no you don't, because you know cosine x is always positive there. If it was between minus pi halves and pi halves, you wouldn't need. Now, let me make a correction there. You could not include pi halves. Anyone know why? Between 0 and pi halves would be fine. 0 would be okay for x, but pi halves would not be okay for x. Anyone know why? The cosine of pi halves is 0, and you cannot take the log of 0. So that's why you have to exclude the pi halves. X equals 0 is fine, so that could be a bracket, but the pi halves would have to be a parentheses because you cannot include that. But if you went all the way over to minus pi halves, then it's parentheses parentheses, because at minus pi halves cosine is also 0. But if you included anything outside of that, but of course you couldn't include a 0 for that, so you couldn't include any of your half pi's anyway. So your limits here would have to be something, if you're between, like I say, minus pi halves and pi halves, yeah, you can leave off the absolute value bars. If you're between pi halves and 3 halves pi, but not counting either endpoint there, you would have to have the absolute value bars, because you would be, those are, cosine is negative there. So that's why absolute value bars are important. Understanding that you can't have cosine x equals 0, which are all your half pi's. Okay. Now, you can take this another step, and let me show you that step. Okay, because this minus sign is out here, one of the, oh, here comes Jalen. I got it before they blacked Jalen's name out. So Jalen's here. Oh, I forgot to admit you. I just marked you, but I forgot to admit you. Okay, so Jalen's coming in fairly soon, I hope. Okay. And by the way, can everyone hear me okay? I think I asked this before. I do have a button here that allows me to what's that again? Oh, is someone not talking to me? Okay, I thought that might help on the drag, but it really doesn't. Okay, all right, here's what we were going to do. Because of the rule for logarithm, if you have a coefficient in front of a log, you can move that and make it the exponent of the argument. So this would be the same as the log of the absolute value of cosine to the minus 1. Now, because the absolute value and the reciprocal doesn't matter, you could move the absolute value, the minus 1 in here, which I think is what I'll do, because that'll make the next, that'll make the next step a little more sense. Make a little more sense. Move the minus sign. It's cosine to the minus 1. Now, here's a problem, folks. It's the cosine to the minus 1. It isn't the inverse of cosine. That's another issue, okay? So this is 1 over cosine. Well, what is 1 over cosine? 1 over cosine is secant. So you could say this is the log of absolute value secant x. Ooh, that's an ugly E. Looks like a beginning writing student plus C. Okay, that's the other way to express this answer. That way you lose the minus sign here and the minus sign raised to minus power. Just make it this. You have to keep the absolute value bars there, because secant, again, like we said, same as before, secant is positive between minus pi halves and pi halves, and secant is absolutely undefined at negative pi halves and pi halves. You don't even have to think about the cosine anymore, just secant. So if it's between those two, you could lose absolute value bars. If it's the next group over, pi halves to 3 halves pi, you'd have to have the absolute value bars. If it was between minus 3 halves pi's and minus pi halves, you'd have to have the absolute value bars, because secant is negative in those two that I just mentioned, positive between minus pi halves and pi halves. Okay. They didn't do that last part. Sorry about that. Okay. But I did. It didn't hurt a thing. Let's see how they did do the problem. So let's move back to our 5.7 and go back to current slide, which is the one we just left, and let's advance from there. All right, that integral does not seem to fit any of the formulas of your basic list. That's why I said know your basic formulas. Okay. However, by using the trig identity, the reciprocal identity, or the quotient identity, not reciprocal, ratio identity or quotient identity, tangent is sine over cosine. Now you have in a form that does look like what you're looking for. If you let your derivative of cosine, you know that's a minus sign. Therefore, you can let x or u equal cosine x, and then you would have the tangent x, the integral of tangent x dx wouldn't be minus this. You'd have to have a minus out here and a minus in here, which is a weird way of doing it, but it's okay, it's correct. If you had done this up here, multiply or divide both sides by minus 1, make that a plus and make this a minus, then you have minus dx d cosine x over cosine x, which bring the minus out here, and you have the log of cosine x, and that's what they got to. Why they like to put that statement in, I don't know. To me, it's not all that instructive, but indeed, if it helps you see it, go for it. It's a perfectly legitimate statement. So that's minus the log of absolute value of u plus c, which is minus the log of cosine, absolute value of cosine x plus c. And they didn't tell you you could move the minus sign up as the exponent of cosine x. That makes it a secant x. So the log of secant x, absolute value of secant x plus c. All right. Now, looking a moment ahead, they are jumping to the next page without doing example 9. So let us do example 9. There's none of this in the slide set, so we'll be strictly whiteboard on this one. Okay. Any questions before I delete this one? Okay. So here's example 9. Let's see if this works better. Find the integral of secant x, and this is a tricky one, secant x dx. And this one basically is like I was mentioning they do before. You almost have to know the answer in order to see how to get there. Okay? And because I've done this many times in my life, I know what the answer is, pretty much. Okay? How in the world are we going to get there? Well, secant is 1 over cosine. That doesn't really help us a whole lot. Okay? But here's the thing that makes it doable. Okay? And this, like I said, you have to know it works before you'd even think of trying it. And here's what you do. And they make it seem like, oh yeah, anyone would have thought of that. Let's take that integrand, secant x, okay, and believe it or not, this is what they do. They multiply it by, of course you would have thought of doing this, secant x plus tangent x, That's a terrible looking C. I haven't even started it, and it's a terrible looking C. Okay. I can get the, there we go. Better, even with the gap in it. You multiply this not by just secant x plus tangent x. But you can't just leave it like that, because that's multiplying by something that's not 1. You have to, if you're multiplying by something, make it something equal to 1. So it's secant x plus tangent x over secant x plus tangent x. Yeah, that was the first thing that popped in my mind, is what you might be able to do to solve that problem. It's a trick, okay? If a trick works often enough, call it a method. So they probably call it a method, okay? So that's what they're multiplying by, that ratio, which is 1. Secant x plus tangent x plus over secant x plus tangent x is 1. And then here you have your dx. So that's the same thing we started with. We just threw that in. Why would we throw that in? Because if you multiply this by, you still got the integral here. It's pretty ugly. Secant x times secant x is secant squared x. Okay, here comes somebody. I think that's James again. I'm thinking James had to leave or check out or something, and now he's coming back in. So I'm here reading it, but I'm not admitting him. So hopefully that's James coming back. James, is that you coming back in? Or is James already here? James, that's you coming back, right?
Yes, sir. I accidentally called by mistake.
Right. Okay. I figured it was you, but they could have more than one person on an iPhone, so just wanted to make sure. All right. So multiplying secant x by secant x is secant squared x. Multiplying secant x plus times tangent x just gives you secant x times tangent x. This is as slow as molasses. Okay, and all that is over, believe it or not, secant x plus tangent x. I'll get there in a few minutes. Yeah. Okay. Oh, I left off my dx, which I always enjoy writing so immensely. Okay. Why would we make this big a mess? I mean, that was a fairly simple looking thing by multiplying by this really complicated looking thing that made this really complicated looking, but can anyone hazard a guess why we would have done that? Because the book told us to, of course. No. What is, okay, what is your, now this is a little tricky. What's the most complicated thing? Anything in a denominator is usually the best answer. So your denominator is the innermost thing. So let's let that be our u. Okay? Let u equal that thing we multiply the top and the bottom by, secant x plus tangent x. Goodness, that's an ugly T. I've got a box over here in the way as well. I'm having to write above it. Oh, goodness gracious, this is so tiring. Okay, anytime you have a let, then you have a then. Now, if u is secant x plus tangent x, what in the world is du? I'm going to have to move the box, I think. Anyone know? What's the derivative of secant x? I'm going to have to move this. Jesus is in the way, of course. Always in the way, Jesus. That's not good. Well, I'll move it again later. It's not bothering you, it just bothers me. What is the derivative of secant x? Anyone remember? Derivative of secant x is, believe it or not, secant x times tangent x. Okay, and then what's the derivative of tangent x? Anyone remember that? Perfect, secant squared x. Oops, I put the square in the wrong place. Let me just put my, okay, secant squared x. Okay, well, what do we have then? This, oh, I've left off my dx. I love writing dx's. Okay. Okay. So the du is secant x tangent x plus secant squared x dx. Guess what? That's your numerator here, right? Just in reverse order. They put the secant squared first and secant tangent second. Doesn't matter. It's commutative. And there's your dx. So there's your du over u. So this is the antiderivative of du over u. And what's the antiderivative of that? Please say you know. What we've been doing the last several problems. Absolute value of log u. Log of absolute value of u plus c. No reason to put any other variable there or letter there, just plus c. All right, now we go back and plug in what u is or r or whatever. I'll try to find a better place for this. Okay, that's a good place for it. Okay. And since your original problem was in terms of x, let's go back and put this answer in terms of x. Well, what's your u? It's secant x plus tangent x. So this is log of absolute value of secant x plus tangent x. I can't get the pen to write. Secant x plus tangent x. Goodness, this is hard to get it to move. Okay. Close the absolute value bars and put your plus c there. Now, folks, that was nothing but a trick. You know, this one, rather than try to memorize or anything like this, pick you up a table and go for it. If you go to the front, let me see if I'm saying this, yeah, front inside part of your book, if you have your book there, and even if you're using a different text, it's probably in the front or in the back. And here's some basic integration formulas, and when you get down to the trig functions number 12 there, the integral of secant u du is the log of absolute value of secant u plus tangent u. close absolute value bar plus C. Write it down, okay? You can remember this trick if you want to. It works. It's certainly doable, but it's a trick. And hold no illusions. It's just a trick. Who would have thought of doing that? Maybe someone would have. Most of the time, that was just a trick, okay? So let's go back to, if I can get it to, and we'll go back from current slide. Okay, we did example 8. We finished example 8. Here is example, the top of page 361. Okay, the integrals of the 6 basic trigonometric functions are summarized below. Okay, because the derivative of cosine u is minus sine u, therefore the integral of sine u has to be minus cosine u plus c. Because the derivative of sine u is cosine u, the antiderivative of cosine u du is sine u plus c. And because, as we just did in example 7, I think it was, the integral of tangent u du is minus the log of cosine u, that's absolute value, and this extra vertical line has no meaning whatsoever. It's here on the slide set. I don't know why it's there. It's not an absolute value bar. It's just something that snuck in there, and the people who were doing the slides didn't notice. I can't get rid of it, but that's an irrelevant, extraneous marking, not belong to the problem at all. Minus the log of cosine u, absolute value of cosine u plus c. Or, as we noted before, you could also write it as the log of absolute value of secant u plus c. Either one of those are legitimate answers. And cotangent and antiderivative of cotangent u du would be the log of, not the minus log, but the log of absolute value secant u plus c. Okay? Same principle that we did. You break down cotangent as cosine over sine. Sine is the u, and go from there. And as we just saw, the antiderivative of secant u du is the log of secant u plus tangent u, and yeah, don't forget to put the plus c. Okay, I get this last one done. Sorry. The antiderivative of cosecant u du, very similar to secant. It's just minus the log of absolute value secant u plus tangent u, all in absolute value, plus c. Okay, excuse me just a minute. I've got to get a sip of water. My mouth is incredibly dry. I've got to remember to move my microphone back before we start again. All right, I think this leads us to, whoa, no it doesn't. I was going to say to examples 10 and 11, but examples 10 and 11 are not done in the text. So if y'all want to see them done, it's whiteboard time again. I can hear the cheers in the background because this we look forward to with so much enthusiasm. Let's clear the drawings out of the way. I'm going to leave this block here kind of in the way, but I'll be writing a little bit to the right of that, so that's why I'm indenting. You can't see the block, I don't think, but I can, and it's a pain in the neck to write around. So this time we're doing definite integrals. Let's see if they're legitimate. The integral from 0 to pi fourths, and if you thought doing this on the whiteboard like this was fun, just imagine what it was like doing on the test bank. I mean on the test, when they gave you just a little bitty window to do your writing on. Okay, it was fun. And here's your square root of 1 plus tangent squared x dx. The x inside the radical, dx of course outside the radical. Now, anyone want to make a suggestion of where we start? Boy, most complicated thing here is the outer function, square root function. Now in the inner function, you have a 1 plus tangent squared x. Before you jump the gun and start doing a u substitution for that, first ask yourself, is that a trig identity itself? And what's the answer? Is 1 plus tangent squared one part of a trig identity? Please say someone knows. Oh boy, who's that trig teacher? Gonna have to do some chewing out. Zero to pi fourths. Well, 1 plus tangent squared, remember there are multiple ways to express the Pythagorean identities. Anytime you have a trig function with a square in it, think Pythagorean identity. Well, one of those is secant squared is 1 plus tangent squared. Now that comes from the fact that sine squared plus cosine squared is equal to 1, right? Divide both sides, everything on both sides, by cosine squared. Sine squared over cosine squared is tangent squared, plus cosine squared over cosine squared is 1, and that's equal to 1 over cosine squared, which is secant squared. So this inside the radical is a secant squared. Well, that's a perfect square, and the square root of a perfect square is just the function. So this is the, why did I start with the e? I don't know. This is the secant x. dx. No substitution. Goodness gracious. I'm staring so hard. My eyes are twitching. Okay. Now, guess what, team? We just did that. Does anyone recall what that was? Please someone say yes. I remember. It's the log of absolute value of, if I can get it to right, secant x. It doesn't matter which order you do these. I'm writing it as I remember it. Secant x plus tangent x. I'll get it there in a minute. Okay. Now, we don't need to do the plus c here because we have limits of the integration. So this is going from 0 to pi halves. No, pi fourths. Can't go to pi halves because neither secant nor tangent is defined there. But they both will go to pi fourths with no problem at all. Okay? Now, and between 0 and pi fourths, secant x is positive, tangent x is positive, so you could have lost the absolute value signs because the sum of two positive numbers has to be positive. So let's plug that in, and that would be the log of, we don't need absolute value bars, so let's just write it. Does anyone recall what secant of pi fourths is? Well, here's a little hint. Secant is 1 over cosine. What is the cosine of pi fourths? Well, we usually write it as square root of 2 over 2, but then when you would invert that, because secant is reciprocal of it, that would just be root 2. So this would be a root 2, if I can get it to write, the square root of 2 plus, anyone remember what tangent of pi fourths is? Wait, here's James, I think. If I find him again, there, he's still here, but I've got to let him back in. I hope that's James. James, is that you coming back? Yes, James? Yeah, that's still you? Okay.
Yes, sir. I kept getting all losing my signal.
Yeah, okay, sorry about that. It looks like mine may be okay, but I know the what you call it, the whole industry, Spectrum and Charter and all these places, they are being stretched to the max, and they are losing like crazy. So sorry about that. Okay. Anyone know what tangent of pi fourths is? Someone say yes, please. 1. Okay. Okay. Now, subtract from that minus the log of, does anyone remember what tangent of 0, secant of 0 is? Secant of 0 is 1, because secant is 1 over cosine. Cosine of 0 is 1, so secant is 1. Plus, oh man, look at that. I didn't even have my finger on, and you see, once it does something stupid like that, it won't erase again. I didn't even have my finger on the button, and it just started writing on the screen. Now let's see who this is. Can anyone tell? I can't read. I'm going to admit them. Is that Kyle? Kyle, is that you just coming in? Is that Kyle? That's who I thought I saw there, but it was blacking me out, so I couldn't tell. Or blacking you out. Was that Kyle who just came in? Who just came in? Could y'all tell who just came in? Maybe you were out and you came back in. Is Kyle here? Let me look at this and see. Maybe I was wrong. Who just came in? Kerpa, was it you or Kira? Because I thought I saw a K.
I've been here. I think you joined and then left again.
Who is that, Kyle?
This is Kerpa talking. I think Kyle joined and then left.
Yeah, I thought it looked like his thing, his symbol, because he's a little K and y'all are big K's, so I didn't think it was you. Okay, but where we were, once this screen screws up like this, it won't think. This is just a 1 here. It just went all over the place on its own. That's just a 1. I can't do a thing with it. Plus, that's the secant of pi of 0, plus the tangent of 0. Tangent of 0 is 0. And here's the good news about that 1. Oops. No, that was my fault. Log of 1 is 0. So that goes away. Here's your answer. Log of root 2 plus 1. That's it. You don't need absolute value bars because radical 2 is positive, 1 is positive, sum of two positive numbers is positive. Okay. and they went so far as to try to figure out what those were. You have calculators, you know how to use it. I'll just verify that they did get it right. Okay. There's just too many moving parts here. All right. And to use a phone for a calculator, you can't do the log first. Most calculators you can, but not this. You have to do root 2 first, and there you have to do 2 first, then the square root key, then add 1 to that, do an equals key, and then do the natural log of that. And that gave you 0.881, which is what they got. Okay, good deal. They got it right. Just wanted to verify. They weren't telling you something wrong. Any questions? Okay, was that someone trying to say something? All right. Let's move on to 11. Now let's see if I can get it to clear. Yes, it would clear. I may not be able to use my eraser anymore, but I can clear. Okay. Here's example 11. Find the average value of tangent x. So here's your f of x. Is equal to tangent x. They are loving this, aren't they? Okay. All right. It says find the absolute value of that function on the interval between 0 and pi fourths. Same limits as we had before. Okay. And if you remember how they said do the average value, it's 1 over the length of that interval, pi fourths, times the integral of that, 0 to pi fourths. And that gives you the average value. So the average value, I don't know how, not a real special way to say it, so I'm just going to do AV for average, VAL for value of this would be, picture the rectangle that has the same area that's underneath the curve, and that's the length of the rectangle is 1 over pi fourths. So actually I'm going to do it, if you don't mind, write that as 4 over pi. 1 over pi fourths is the same as 4 over pi. Okay, and then the integral we just, no it isn't, starting to say the integral we just did. The integral we did not long ago in example 8. Okay, and rather than going through all that again, go back and look at example 8. But in example 8 we found that this was times, and I'm going to write it in the form that I left it as, the log of, and because 0 to pi fourths, the secant is positive, that would be secant x okay, I don't need brackets there, 0 to pi fourths. That's the 0 down there. Okay, so this would be your 4 over pi, which is 1 over pi fourths. It's a number just a little bit more than 1, not a whole lot more than 1, but just a little bit more than 1. And this would be the log of, And secant pi fourths we just did not long ago to be the square root of 2 minus the log of 1. The log of 0 is 1. No, I'm sorry. No, secant of 0 is 1, and the log of 1 is 0. So that's why I wanted to leave this off. So there's your answer. 4 over pi times the log of root 2. Okay? You don't need absolute value bars because root 2 is positive. Okay? Now, they wrote it differently, weirdly, with the minus sign and the log of root 2 over 2, but you'll see this is the same answer. Let's go back to my calculator, turn it sideways to get the thing in. The way I wrote it is, I think, much simpler. 2 square root of 2, 1.414, blah, blah, blah. Take the log of that, ln log, natural log of that, and then multiply that by 4 and divide it by pi. And you get 0.412, blah, 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 4412, blah, blah, blah. Okay, and that's the same thing they got, just a lot easier using secant than minus log of sine, or cosine. Okay. Finally, we did finish 5.7. That's been long enough, hasn't it? Homework exercise here would include any of the odds 5 through 27. They're all at CalcChat, 9's at CalcView. Any of the odds 29 through either 29 or 31, they're both at CalcChat, 29's at CalcView. Any of the odds 33 to 41, all at CalcChat, 33's at CalcView. Either 43 or 45, both at CalcChat, 47's at CalcChat, 49's at CalcChat. Any of the odds 51 to 57, they're all at CalcChat, 55's at CalcView. 59's at CalcChat, either 61 or 63, both at CalcChat. 65 or 67, both at CalcChat, 67's at CalcView. 69 or 71, both at CalcChat, 69's at CalcView. 73 or 75, both at CalcChat, 73's at CalcView. 77's at CalcChat. 79, if you want to look at it, is at CalcChat, should be. Then there's either 81 or 83. Both should be at CalcChat. 85's a proof that should be at CalcChat. But go back to 81 for just a moment. Napier's inequality. Okay? Does anyone recall, or have you ever known who, I think it was John Napier was? Or, yeah, was. If my memory's right, I think he may have been Scottish, but he may not have been. I don't recall for sure. It doesn't sound like a Scottish name, but the Scots and the French were fairly close, so he could have easily been Scottish. Okay. I think he was a minister, believe it or not. But if you think back at the time when he was living, ministers are sometimes some of the most educated people that were around. And he's the one who developed logarithms. Okay, so it's not surprising he would have an inequality that refers to logarithms. So you can either choose to write on Napier, since he shows up in our text here, or how did he develop this inequality, or when do you ever use this inequality? Any of those would be legitimate paper topics. So moving on. I said you could do the proof 85 if you chose, should be at CalcChat. Then do any of the odds 87, either 87 or 89, they should both be at CalcChat. 91's a sort of practical problem, as is 93, as is 95. So you can choose any one of those three or more of them if you chose. They should all be at CalcChat. 97 and 99 are both true-false questions. You can certainly take a look at those if you'd like. And 101 is another proof if you're interested in that. All right, any questions 5.7 before we move to 5.8? So I'm going to go back to my thing. We're through with 5.7. So I think this is 5.8 here, though it's blacked out. That doesn't seem to be 5.8, or is it? No, I don't think so. No, that's 5.7. Let me go back. I had 5.8 up here. And now it's nowhere to be seen. That had been 5.8 before, but that's still 5.7. That's 5.7. That's nothing. That's nothing. That's Screencast-O-Matic. That's something. I'm pretty sure that's 5.7. So I'm going to have to abandon you for a moment here. And so hold on. You're going to lose the screen share for a moment. Let me try it one more time and let's see if anything new pops up here. Let's see, maybe it's here. No, it's not there either. So let me go back to, tell you what I'm going to do. I'm going to cancel this one. Screen sharing stopped, I realize that. I've got to go back here to my computer and go back to my flash drive. All participants. I've got that we've got 11 now. 1 or 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, we've lost 2 people. I think Kyle was one. I don't know who the other one is. Okay, sorry about this. Having to go back and get this to reopen. I tell you, it was there. I saw it a couple of times when we were doing other things. It was there. But now it's not. Now it's back. So let's do the slideshow from current slide. All right, still in Chapter 5, Integration. 5.8 is inverse trigonometric functions, integration of these. Okay? Doesn't sound too promising, does it? It really isn't as bad as what you would think. And there's a good reason to do it now because we're going to be doing more of it later. Integrate functions whose antiderivatives involve inverse trigonometric functions. Okay, that's a mouthful and it sounds like it's undoing and redoing something rather bizarre. You have an inverse and an anti. They're similar but not the same. Use the method of completing the square to integrate a function. That'll be sort of a new one. And we'll review the basic integration rules involving elementary functions. We're not going to deal with non-elementary functions. So let's start with integrals that involve inverse trigonometric functions. The derivatives of the 6 inverse trigonometric functions fall into 3 pairs. In each pair, the derivative of one function is the negative of the other. The derivative of an arc sine is exactly the same as the derivative of an arc cosine, except the arc cosine is a negative. Okay? But other than that, they look the same. Okay? Now, here's what you're going to get out of here. Therefore, when you see something that looks like this, here's your trig substitution. Now, they're probably not going to do it this way, but it really is the easier way to go. You say let x, now you're not doing a u, let x equal sine of u, I guess you would say, okay? No, let u equal sine of x, okay? But just think it, no. I like it better the other way. Let x equal the sine of u. Think of it that way, okay? Because this is the inverse of that, okay? The next pair, when using the antiderivative that corresponds to each of the inverse trig functions, you need only use one member from each pair. Use the positive, okay? The arc sign rather than negative arc cosine. Why throw an extra minus sign in there you're going to forget about? The minus signs are only there to trip you up, so don't get confused. Here's another pair, arc tangent. Notice how that is. It's something that's always a squared plus u squared. The arc sine is a squared, the square root of a squared minus u squared in the denominator. The arc tangent is a squared minus u squared without the square root, only this is plus u squared. And then the arc secant, again, is u times the square root of u squared minus a squared. Okay, now notice the difference between these two. This is a squared minus u squared, this is u squared minus a squared, and this also has a u in front. That's going to be the dead giveaway for arc secant, this will be the dead giveaway for arc sine, and this will be the one for arc tangent. Okay, now these all basically come from your Pythagorean identities. Okay, just picture the a as being a 1. 1 minus sine squared is cosine squared. Picture that as being a 1. 1 plus tangent squared is secant squared. And picture these being 1s, or at least, no, the a being a 1. This is, if you let secant u equal, they change the variables around on me, but think of this as a secant squared minus 1, that's going to be a tangent squared, okay? And then you take the square root of it. So that's how I remember how to do these. This is Pythagorean identity, basically sine squared minus cosine squared, or plus cosine squared is equal to 1, so 1 minus sine squared is equal to cosine squared. 1 plus tangent squared is equal to secant squared, and secant squared minus 1 is tangent squared. Okay, if you remember those, that will help you know which way to go. Okay, so I don't know, to me these aren't worth memorizing, but if you wanted to, you certainly can. Let me show you, and we're going to do this a little bit later. Well, I guess right now just look them up. That's all they're saying doing. Okay, but I do want to tell you how to do this. Here your substitution would then be let x equal sine theta. I don't like to use a u there, make it a theta, so that's what I'm going to do. Oops, I can't write here. Let me get my, oh, y'all can't see this, so y'all are just going to sit there and let me talk with this and not bring the screen back. Okay, y'all let me know. I realize now we weren't screen sharing. I went to get it, but here it is. Okay. I think this will work. Okay, here we go. Now, let me do two things at once. I'll first bring in the whiteboard. Okay, and I'm going to get this out of the way. Yuck. You can't see this, but it's a toolbar, taskbar. It's at the bottom of the page. It just gets in the way of everything. So that's done. And then this taskbar is in the way of everything. So I'm going to move it up here as far as I can here. All right, and let's clear my drawings. Okay. Now I think I'll move, you can't see this either, but this block of people over here. So let me get back to here. Here is the first one. The integral of dx over the square root of, and basically all you have to do is go back and check and verify this with the identities they gave you. 4 minus x squared. But I wanted to show you how to do that as well. Okay, that's what we do. And they just wrote down the answer, and that's all you did. That's x squared. Okay, so here's what the identity is going to be. Let x now, not u, x, that's the variable that's in here, equal to, now here's the rub here. We really want that to be a 1. How we undo that is take the square root of this 4, that's a 2, and write that as the coefficient here of your x. Now that seems magical, mystical. Why would you ever think of doing that? Don't question, just do it. Okay, that would be sine of some angle theta. Okay, now, okay with that. Of course, anytime you got a that, follow it with a then, a let, follow that by then. Then dx, which is what you have up there, so we want to know what it is. Dx is equal to, and what is the derivative of 2 sine theta? Two times the cosine of theta. See, that's the other reason to stay with sine, because its derivative is positive cosine. All right. Now, up here we don't have just a plain x, we have an x squared. So let's figure out what x squared is. X squared, from here, if x is 2 sine theta, x squared would then be 2 squared, which is 4 sine squared theta. This is so tedious writing, it gives me a headache. Okay, so there's your x squared, but we just don't have that. We have a 4 minus x squared. So let's write down what that is. 4 minus x squared well, 4 is just 4 minus what we just found out x squared was 4 sine squared theta. Okay. Now, before we go any further, we know something about that. We can factor a 4 out of both terms of that, can't we? So let's do that. That's 4 times 1 minus sine squared theta. Now please someone tell me that rings a bell, and you know a trig identity that tells you exactly what that is. What is 1 minus sine squared theta? Anybody? You got it. So that would be 4 times cosine squared theta. Now, remember, this is all what this is, 4 cosine squared theta. That's what's under the radical here. So the next thing I'm going to do is I'm going to put a radical over this, and that also puts a radical over this. It would everything in between, but we're already through with that. And what's the square root of 4? 2. And what's the square root of cosine squared? That would just be cosine. So that radical just turns out to be 2 cosine theta. That's what's in the denominator. So now let's write again what we've got here. The dx is 2 times cosine theta. And you let me get away with it and didn't do it. You know what I'm talking about? Here I did a d and didn't put a d over here. This is a d theta. So our dx is the integral of 2 cosine theta d theta and that's divided by that radical, which is 2 cosine theta. Guess what, team? Everything cancels out except the d theta. This is just 1. Okay? And what's the antiderivative of d theta? Theta plus some constant. But what is theta? Well, theta is, from up here, we did what x was. Let's do it in reverse. X over 2, divide both sides by 2, is equal to sine theta. And then solve for theta, and you do an inverse sine. So theta is equal to inverse sine. I like to write it as inverse sine. The book likes to do arc sine. To me, arc sine is really archaic, of x over 2. Okay? And then you have your plus c. Because this was theta plus c, so theta plus c. So that's how they get it. They write it as inverse sine, as arc sine. I wrote it as inverse sine. Same answer, folks. Okay? Now this is how they get it. What they do is just say, here's what it is. Okay? Now, if you want to just memorize the formula and write down the answer, you can. But let me tell you, most of the time they're going to have something else complicating that, and you're going to have to do a substitution a lot like we did. But this is a different kind of substitution. It wasn't a u substitution. It's u is introducing a new variable to replace something in your integrand. This time we're taking something from the integrand and let that represent a new function. Okay? So that's the reverse of what we've been doing. So you just have to keep that in mind. So let's go back to our this one. Okay? And they're just saying, here's what it, the integral is. If you remember the formula it just gave you, let u be x and a equal 2, and this would be the inverse sine of x over 2 plus c. Well, that to me is either a memorization or look it up in a table. One or the other. If you want to know how you got it, I just explained that to you. Okay, the B one, they're doing the same thing, only this time it's that inverse tangent form, because here you have an a squared, though it's not a perfect square of square root of 2, so that would be your a would be square root of 2 plus 3 times x squared. 3 times, well, it's 3x squared, okay? So this is square root of 2 squared, and this will be a 3x squared. Now, again, they're requiring you to remember what the formula is to make this look like the formula. And that's perfectly fine. That's what you do when you look up in a table. What does this resemble? Well, with that, here's what they've left off here. Then du is equal to 3dx. So you put a 3 up here with the dx and a 1/3 on the outside of the integral to make it 1/3 of 3, which is just the dx you had to begin with. And then this form, so that would be 1/3 your inverse tangent of root 2, root 2 times the inverse tangent. Well, it's just too much to memorize. This is how they say to do it. The 1 over 3, and they don't really tell you where the 1 over root 2 comes from, except from the formula of the arctangent of 3x over root 2 plus c. That other one is, I don't know. To me, I hate memorizing. I would never do it this way. If you want to do it the other way, I'll show you how to do it, but this is the only place this shows up. Uh, Later when we get to this in techniques of integration, we'll do it the method I'm trying to show you, I showed you in the last one, and it's just so much easier to do than trying to memorize a formula. So for right now, just use the formulas, plug them in. And that's to go back and see what formula that is. That's this one, the second one here, and you see it's 1 over a, where a is this thing, arctangent of u over a. So the 1 over a, that's 1 over root 2. Okay, but then because you have a 3x as the u, then you have that 1/3 in front. So that's what makes it a 1 over 3 root 2. And that's where you get this. Okay. All right. And again, this is just like looking it up in a table and then making it fit. And that's perfectly a legitimate thing to do. It's what I do a lot, okay? I don't sit down and memorize these things. I look them up in a table, okay? The C one is using your secant function one. Remember, this would be the secant of 2x, because it was u squared, so that would be 2x. So you have to have a 1 over 2 in front and a 2 up here too. They didn't pull the 1 over 2 out front. They left it here because that is your u was 2x now. Okay, 2x squared plus 3 squared. So if you multiply by 2 here, multiply by 2 there, same thing you had before, and this then would be 2 times the inverse secant of 2x over 3. Okay. Oh, I forgot. You have the 1 over 3 from here. I forgot that one part. 1/3 arcsecant of absolute value of 2x over 3. The reason you need the absolute value here, they haven't told you before. If this thing did turn out to be negative, well, it couldn't be negative. Well, I guess their formula, yeah, it did have an absolute value of u there. Okay. And here's the reason for that. We never, or I never deal with arcsecants anyway. But the arcsecant function is such a weird looking function. You almost have to have the absolute value thing in there, because if you introduce another half of it, you'd be on the other side there of what the arcsecant was, and that would, it's not defined there. So you have to use absolute value bars. And again, if you want to memorize the formulas, write them down from here. If you want to do the other way, just hang on. We'll get there later. Okay, and you'll see the easier way to me than memorizing. Okay, so that's all we're going to do with that one. Now, completing the square. This is something you've run into in the past. You're going to run into again, over and over again. We're going to be completing squares. Completing the square helps when quadratic functions are involved in the integrand. Okay, for example, x squared plus b squared plus c squared can be written as the difference of two squares by adding and subtracting b squared, b over 2 squared. Okay. Now this to me is, again, the strange way of doing this, okay? But what you're doing here, if you're completing a square, you take half of this middle term, that would be b over 2, square it and add it to the other side, and then subtract it. And that's what they're doing here. Okay, the c, get on out there out of the way. So just get your x terms together. X squared plus bx. Let me do this on the whiteboard because they sort of have it so botched up here. It's hard to talk through. Okay. All right, to clear this, we're through with it, right? Okay. Let's go back and do this the way. What was it? Oh, they skipped example 2 and 3 before they got to completing a square. Let's do those. Sorry about that. How are we doing on time? We go till 2:30. Okay, so we got plenty of time. Let's do example 2. Okay. Here's the integral, okay, of dx over the square root of e to the 2x minus 1. Okay. Now, that really doesn't look like anything that we're talking about before. Okay? But it's not as far removed as what you might think. Now, if that was your issue here, what might you choose as a substitution? Now, back before this section, probably you would have said, let u equal e to the 2x minus 1. Okay? Then du would be e to the 2x times the 2. 2e to the 2x. Well, you don't have a 2e to the 2x in here. That would fall apart. The regular substitution doesn't work well here. So here's what we do instead. Let's do, going back to the very basics here, find the most complicated thing. That's your denominator. Okay? Find the innermost piece for that most complicated portion. Well, that would be the exponential function, but not e to the 2x, just e to the x. So that's going to be my first step. Let, now sometimes this won't be necessary, but you'll see when it won't be, and you haven't lost anything. Let u equal e to the x. Okay. Now that implies that u squared is equal to e to the 2x. Agreed? You squared this side and squared that side. So now what you have in your denominator is a u squared minus 1. Okay, let's see the best way to proceed with that. It sure looks like a little bit like a secant, and I know that's where they want us to head, but I was trying to think if there's an easy way to get there than what I'm sure they want us to take. Let me think on this just for a moment here. Let's proceed down here. Maybe something will pop into, see if there's a better way to do. Always follow the let by then, and this then is always then your du is equal to e to the x dx. Okay, now this isn't looking promising, is it? Okay, which though would be u dx, isn't it? Because e to the x is u. Well, let's get the u back here. So divide both sides by u. So du over u is equal to, this is a big long equal sign, we divided both sides by u, dx. Alright, so what do we have now? This will be the integral of, the dx is du over u times the square root of u squared minus 1. There, I've done it. I've made it look exactly like an inverse secant. Okay, if I wanted to, I go back and do the long way around doing this, but let's just end it here. Not end it, but satisfy that is, if you flip back one page, you see that is the inverse secant of u. No 1 over anything involved, I don't think. Yeah, there's no a is 1, so this is inverse secant of u. Now, be careful here, folks. This is an inverse secant, and that's why they like, I think, to put arc secant so you don't get it confused for 1 over secant. Inverse secant of u, okay, and that would be a plus c too. We can go on and put that down. Okay, plug in what u is, that's the inverse secant of e to the x. Plus c. Now, do not think that's 1 over cosine. It isn't. That's the inverse secant, or the arc secant. And that is what they get the answer to be. They use the term arc secant. I guess the reason they do is so you don't confuse it with 1 over. Okay. Now, they have a little blurb there in the middle of the page. This is page 366. Technology pitfall. And I'm not quite sure where they get this. They're saying if you rewrote that as the arctangent of the square root of e to the 2x minus 1 plus c, that's an equivalent answer. It seems like a lot more complicated, so I see no reason to pursue it. Let's move on to example 3, unless someone has an objection. Any questions on that one? Please speak up if you have a question. Okay. Example 3. This is also not on the slide set, so let's do it here. The integral, or the antiderivative of x plus 2 over the square root of (4 minus x squared) and all that's by dx. Now, for some reason I get my, okay. Here's something to watch for on these. Please don't think there's any way you can get that numerator somehow out of taking the derivative of the denominator. It's not going to work, or any part of the denominator. What you have to do with a problem like this is split it. Okay, and here's what I mean by that. The first part of this is going to be the integral of x over the square root of 4 minus x squared dx. The second part is going to be a plus 2 times the integral. I took the 2 on the outside because I don't think we need it on the inside. And I'm just going to put the dx up here over the square root, because the denominator is the same on both of them. Okay? 4 minus x squared. This is so tedious writing this. Okay, now, this is a regular old u substitution. This first integral here is a regular old u substitution. And here, we'd go back to what we did years ago, it seems like. Let u equal the innermost part of that most complicated part, that's your inside the integral. That's equal to 4 minus x squared. Okay, that's your u for that part. Okay. Now, of course, you follow the u with a then. Du, it's pretty ugly looking, isn't it? Okay. Du is equal to, what's the derivative of this thing? Minus 2x dx. Well, guess what? You don't have a minus 2x dx, you just have an x dx. So let's divide out our minus 2. Dot it on that side, you divide it on this side as well. Okay, so that first integral is going to be written in terms of u now. The du is going to have a minus 1/2 in front, so that's what I'm going to put here. Minus 1/2, and then this will be the integral of du, because that's what we've got left. When you divide out the minus 2 here and the minus 2 there, you have the x dx, which is just du. Goodness, this is giving me a headache. Over, now, this was a u inside the radical. So I guess I'll leave it inside the radical, but I just going to write it. I'm not going to leave it inside the radical. I'm going to write that as u to the 1/2, because that's what the radical means. U to the 1/2. And I don't like the way that looks either, so I'm going to bring this down and say this is minus 1/2 times, okay, lost my microphone there for a moment, the integral of u to the minus 1/2 du. I don't like integrating with things in the denominator, as you probably can tell by now. Well, why does that integrate? This is simply u to the, up that by 1, this is a power rule, okay? Up it by 1, you get 1/2, divide it by that 1/2, which is basically multiplying by 2, and guess what? The 2's go out. The minus sign doesn't, but the 2's go out, and then you have a plus c, because you don't have a, whoa, that's an ugly c. So basically this side is minus u to the 1/2, or minus the square root of u. Well, what is u? It's 4 minus x squared. So let's just do it, the square root of 4 minus x squared. I'm going to leave off the plus c for now because we're going to have another one coming up in just a minute. So let's do this side. Well, look at that. That's basically your inverse sine, except it's not a pure sine because you have an a down there that is 2 squared minus x squared. So this will be inverse sine of x over 2. Okay? Yeah, inverse sine of x over 2. So this would be, I'm just going to come on down here and write it in, plus 2 times the inverse sine. And it's not that I have anything really against arc sine. It's just a lot easier to write inverse sine of x over 2. And now I'm going to put my plus c. No reason to put more than 1. So that's our answer. Now that's just a square root sign. All that mess at the front, I don't think I can erase. Yeah, the eraser's not working, so I can't do it. So let's see what they got. Minus the square root of 4 minus x squared plus 2 inverse sine x over 2 plus your constant c. Okay, good deal. All right, 129, we have about a little less than an hour to go. So let's go back to our PowerPoints, and we were go back to current slide, and here was completing the square. Oh, and that's what I was going to show you before I turned the page. Let's go back and do this on the other page. What they did is correct, but it's just really hard to follow when they write everything on one line at once. Okay, so here's what you got. Now this is really the simpler form of completing a square. Okay, the square they're trying to compete is x squared plus bx plus c. Okay, trying to complete the square. Okay, now maybe just a little bit of review. Let's just review real quickly what x plus, give me another letter, not A, B, or C. Some other letter. Anybody? Anybody? Pick a letter. Letter. A letter. Not A, B, or C. Any other letter. No X, not an X. Probably not a Y or, say again? C. You say Z. T, T. Oh, fine. Perfect. X plus T. Now let's square that binomial x plus t. Okay? Now, square it. Okay? Now here's the easy way. If you want to FOIL it, you can, but the easy way, square the first one. X squared. Okay? Plus 2 times twice the product of the 2. Plus 2t. Now t is just a number, remember? Times x. And then square the last term. Plus t squared. Now that's squaring a binomial. That's the perfect square of a binomial. Okay. Now, what we want to do is get this binomial to look something like this. Now remember, t is just a number. Don't worry about what number it is. It's just a number. So here's how you go about doing it. Well, let's take this one up here. How would you figure out what the x plus t was? You take the square root of this, put it there. You take half of your coefficient here. Half of 2t is t, okay? And put that here, and then put it in parentheses and square, okay? And that's what gives you this, okay? Now, let's kind of undo this. First thing we're going to do is take half of this coefficient, and that's going to be b over 2, okay? Now, what are we going to do with it? Okay, now we can't quite do that. We just changed the problem. Okay, so what we're going to do with that is let's just, okay, let me back up one. I don't like the way this is heading. Oops, I can't do that. I'm used to going down there and picking up. Okay, forget I did this. Okay, forget that. Okay, let's just separate this from that. So this is going to be x squared plus bx, I didn't mean to have that much room, then put a big old blank there and put our c. Now the only thing I did there was spread out our problem. Okay, now here's what we're going to do here. We're going to take half of this b, just like you take half of this 2t here, and square it. Okay, so 1/2 of b squared would be plus b over 4, b squared over 4. That's taking half of this b over 2, and squaring it and adding it here. Well, if I add it there, I also have to subtract it here. B squared over 4. Okay. Now, this I know to be the perfect square, because that's exactly what I did here, of x plus b over 2. That's ugly 2. And then you got this left over. Now this is a perfect square of that. C minus b squared over 4. All right. Now, do you believe I just completed the square? Well, let's try it. Square the first term, x squared, plus twice the product of these two. Twice b over 2 is b times x. There's your bx. Plus this thing squared. There's that thing squared. Okay? And you subtract this from both, add these two together, you get 0. You're back to exactly what you started. So we just completed the square with this part here. And that's why they went through the thing of saying you adding and subtracting square b over 2 squared. Yeah, that's what you did, but this is why you did that. Now maybe this makes no more sense to you, but let's do example 4. Yeah, let me erase this. Excuse me, let me get something else to drink. For those who follow this type of stuff, summer solstice was yesterday, meaning officially we are in summer, and this room upstairs is feeling like it's summer. It is hot in here. I've got the ceiling fan on. It's still hot. Most days I've had to turn that off because it gets a bit too cool. Not today. All right. So here's example 4, and if you don't have a book, you can go to larsoncalculus.com and see an interactive version of this type of an example. Okay, so here is your integral. Dx, it's an ugly D, over x squared plus 4x, x squared minus 4x plus 7. X squared minus 4x plus 7. Okay. Now what's problematic in this is, number one, there's no u substitution you could do, because if you said the denominator was u, then du would be 2x minus 4. There's no 2x minus 4 up here times dx. So that won't work. So here's where we try completing the square. Oops, here comes somebody. Can you tell who that is? Joy Robinson. Okay. I happened to get it right, make it flash. Joy Robinson is here. All right. I can't get my pen to write. Okay, got Joy here. Okay. I think that's, oh, I thought I admitted her, but evidently it didn't admit. Let me try it again. Okay, hopefully she got in that time. I must have hit the wrong key. All right, here's what we're going to do. We're going to come over to the side and complete the square of that. Okay, and here's how to do it. X squared minus 4x. Separate those off by themselves. Leave a big blank there, and then put your plus 7. This is far easier to do in numbers than it is with letters. Okay? Now, I want to complete this square. What do? I take half of the minus 4, and that's a minus 2. And by the way, on the line below here, I put an x, and when I take half of this b, that'll be minus 2. I put that down right there. Okay? Now, half of minus 4 is minus 2. When you square that, square of minus 2 is plus 4. Well, I just added 4 here, so I've got to subtract 4 here, or else I've changed my whole problem. Now it's the same problem I had before. I just added 4 here, subtracted 4 here. That's why I left a big blank there. And I'm going to close this in and put a square here. And sure enough, x squared minus 4x plus 4 is exactly the perfect square of x minus 2 squared. Square the first, twice the product of the two, square the last. That's it. So this is x minus 2 squared, and that's a plus 3 then. 3 minus 4 is 7. I mean 7. 7 minus 4 is 3. I don't know what I'm saying. Okay, so what does this become? This becomes your integral of dx over x minus 2 squared plus 3. Okay, because this thing came out exactly that. Okay, this denominator here is exactly that denominator there. I mean, multiply it out and see. X squared minus 4x plus 4 plus 3 is plus 7. X squared minus 4x plus 7. That's exactly that. But now we've written it in with a completed square in there. Well, that looks a whole lot like an inverse tangent function. And that is indeed what it is. This is the inverse tangent. The book likes arctangent. I'm going to write it as inverse tangent. Okay. Of. Okay. X minus 2 is your argument here. Over root 3. That's a pretty ugly root 3. If you go back one page, and you have to have that 1 over root 3 in front as well. If I could get my pen to write. That's ugly root 3. Okay. There is your answer, plus C. All right. Let's see how the book did. One over root 3, ugly as it is, times inverse tangent, they call it arctangent, of x minus 2 over root 3 plus c. Perfect. Okay. Now, leading to the next step, and I know we've only got about 45 minutes to go, but I think I'm going to have a bladder break. Sorry about this. Are y'all okay with that? Let's just take a quick pause. I'm going to stop the recording, but we'll leave Zoom on, but I'll be right back. I just need to run to the rest. Now, what we had just done was really the easy completing the square. That's when the leading coefficient was 1. Okay? When the leading coefficient is not 1, you have an extra step or 2. So I think I'll clear this screen, if I can get my cursor to show up. There it is. And let's do one that's not 1. Here's the quadratic. 2x squared minus 8x plus 10. Okay. Now this quadratic, we want to complete the square. We don't like having that 2 there. So here's what we do. Again, same as before, separate the terms with x in it from the term that doesn't. Leave a gap there. But not just that, we factor out that leading coefficient. So that'll be 2 times x squared. That's 2 out of the 2x squared, but 2 out of the minus 8 will leave us minus 4x blank, close that parentheses, and then put our plus 10 out here like we did before. That's exactly the same thing as we have here, only written really squirrely. 2 times x squared minus 8x plus 10. Yeah, that's it. Write down the 2. Bring it down. Okay? Now, complete this square. Okay? I'm going to put the x. I know it's going to be there. Half of this term, that's going to be a minus 2. I'm going to write that down right here too. Okay? You take half of this term, it's minus, half of minus 4 is minus 2, square it, that's a plus 4. Well, now I've just messed up this side. Not only did I add 4 here, I have 2 on the outside, so that's adding 8. So that means over here I have to subtract 8, just so it all work out. And indeed it does. If you went back and did these steps, 2x squared minus 8x plus 8 plus 10 minus 8, that adds to exactly what we have here. So we haven't changed that top form, just make it look stranger. Okay, what do we have here? The 2's in front. This is the perfect square of x minus 2. When you take the square root of this, write it down. When you take half of this, write it down, and then you completed your perfect square. Over here, plus 10 minus 8 is plus 2. Okay, so there we have completed a square again. Okay, now that works really nicely when this leading coefficient for your x squared term is also a factor of this one. As you might guess, life isn't always that nice to you, and the next example shows one that wouldn't be that nice to you. Here is, why did they write it this way? Okay, it's okay. 3x minus x squared. I don't know why in the world they would have chosen to write it that way. First thing I would do is turn this around and write it as a minus x squared plus 3x. Now notice you don't even have a constant term on this one. Okay? Now, what you got to do to complete the square is factor out that coefficient of your x squared. In this case, it's a minus 1. That's going to be a minus 1, or you could just leave a minus there if you wanted to. And then this would be x squared minus 3x. Okay, and I'm going to leave a blank and close it off, even though there's no constant out here. It's okay. Bring down the minus 1, and then just like we did before, of course the square root of that is going to be x, so that's going to come down. Half of minus 3 is minus 3 halves. And you can take that, close it off, and this is going to be your completed square. But you got to finish up here. Half of minus 3 is 3 halves. Square that, and you get plus 9/4. Square 3 halves, and you get 9/4. Now that's the 9. Here's the 4. They look fairly close to each other, but they're not. But if you added, you subtracted 9/4 here, so you add 9/4 here. Okay, so this then would be plus 9/4. Because this is the perfect square. This is the perfect square of that. The minus sign here, plus 9/4. So this is the completing the square for one that has a negative in front. It has a second coefficient that's not a factor of the first one. It has all those issues in it. Why they left it as 3 halves squared rather than write it as 9/4, I don't know. Minus 3 minus 3 halves squared. Yeah, they wrote it differently. All right, let's get to example 5. I think we'll be coming right back to the whiteboard, but let's see what they got on example 5. Okay. All right. Oh, did we go over this one? I guess we didn't. Sorry about that. Let's do example 4. I don't think we did that. You can write the denominator as a sum of 2 squares, as shown. Now, that's what they're calling it. Okay. Now, what they did, they separated out this plus 7, put it over here. Okay. And just using the x squared minus 4x plus a blank, okay, in that blank, what you do is take half of this, half of the minus 4 is minus 2, square it, you get a plus 4. That's where that went in. And then the minus 4, I put it on the end, they put it in front. It doesn't matter where you put it, but that goes outside the parentheses. Okay, so this is the perfect square of x minus 2 plus 3. And there it is, x minus 2 squared plus 3, which now they're going to call your u squared plus a squared, because that's what's in your denominator here. Okay, that will be your inverse tangent rule. Let me keep forgetting to hang this back on my pocket. Okay, this will be leading to the inverse tangent rule. So let's see what it is. Now in this completed square form, let u equal x minus 2 and a equal the square root of 3. That's here. U is x minus 2 and a is the square root of 3, because a squared is 3. Okay. So this integral then becomes the integral of dx over x minus 2 squared plus 3, which would be then 1 over root 3, 1 over a, arctangent of x over a, x being x, or u over a, where the u is x minus 2 and the a is square root of 3 plus c. Same thing we got. And now they skip example 5. So let's go back to our whiteboard and let's us do example 5. Are there any questions? Y'all are awfully silent. Someone was asking me over the weekend, it was my parents-in-law, was I missing the class? And we actually had a department meeting too. And the question was, do y'all want to go back to class? And I said, I want to go back to class because I want to see the students. I want them in front of me. I want, when I ask a question, I won't say force, but get someone to answer. Y'all are just too quiet. Please, why don't you speak up, and go. But here's example 5. Let me erase it because I just feel like I'm doing all the talking and I hate it when I do that. Find the area beneath the region bounded by this graph. Okay, and why that showed up there, I don't know. I'm just going to clear the drawing again so it won't show up. Okay, now here is the function. F of x is equal to 1 over the square root of 3x minus x squared. We've seen that before, haven't we? The square root of 3x minus x squared. That's the one we just did, that we completed the square. Okay? Now, if you remember how that completed the square, I don't know if you remember this or not. I don't know if you were paying. Yeah, that's an ugly one. How that completed square was, I'm going to write it the way I did, and then I'll turn it around and write it the way the book did. I had a minus here, and our completed square was x squared minus 3, x minus 3 halves. I can't erase. This aggravates the fool out of me. Okay, I shouldn't make mistakes, but I do. Okay, that's an x. That's just a blob up there. Pretend it's not there. X minus 3 halves, remember? Squared plus 9/4, I believe it was, wasn't it? I'm doing this strictly from memory, but it seems like that's what it was. Okay, now, the book writes it the other way, which is, in this case, more convenient for what we're going to be doing. 1 over the square root of 9/4, which remember was the square root. It's 3 squared over 2 squared. So it's the square of, that's a 9 and that's a 4. Unfortunately, this makes them look too close to each other. 9/4 minus this quantity, x minus 3 halves. Squared. Okay, the radical comes out there, the dividing line comes out there. Okay. Whew. My hands get cramped with this tedious writing here. Okay. Well, this is your inverse sine form. Okay. Where that is your a squared, which means a would be 3/2, and this is a minus Humpty squat here. So what this would be an inverse sine. The answer of the integral of this, if you were to take this and integrate it with respect to dx, which is what they're asking us to do, I think. Let me go back and read the problem. Find the area of the region bounded by that graph. The lines x equal 3/2 to x equal 9/4. Okay, so we're integrating that from 3/2 to 9/4. Okay, and the x-axis, that's everything above that. Okay, now my nose is itching like crazy. We must be going to have company. Okay, this gives you the inverse sine, and here, rather than go through the stuff that I was telling you about before, just flip back a page and you see you've got the square root of the a is 3/2, arcsine of the u here is x minus 3/2 over 3/2. Okay, so that's the inverse sine. Okay, 1 over a. Remember, your a was 3/2, so 1 over that is 2/3. So this is 2/3 the inverse sine of, and that's the inverse sine, don't let me forget to do that. Goodness, my nose itches. Okay, and your numerator is your x minus 3/2. It's a pretty ugly 3. Okay, that's a 2. Okay, that's your numerator over 3/2 from here. So again, that would be a 2 here and a 3 down here. Okay, and that's evaluated from 3/2 to 9/4. Oh man. Now, I'm going to pull the 2/3 out in front. Okay. Sorry. All right. 2/3 out in front. Now, let's just do this. The inverse sine, if I can get the pen to write, there it goes. That's ugly. Of, okay, this 2 is in front. I'm just going to put this 2/3 here too. It's just easier than dragging it around somewhere else. Okay, now, when I put in a 9/4 here, that would be 9/4 minus 6/4, okay, which would be 3/4. Okay. Okay. Minus, when I put a 3/2 in for the x, that's 0. Okay. Now, I'm sorry. You let me get away with that, didn't you? This is an inverse sine. okay, minus the inverse sign of 2/3. I did it again. Times, and what we just said, if you put in this, that gives you a 0. Okay, and the good news here is 2/3 of 0 is still 0. Inverse sign of 0 is 0, so that's not going to contribute anything. Okay, so this last term contributes nothing. Okay, it's going to be a 0. Over here in this term, this would be a 1/2 here, and the 3's cancel out here, and you get 2/3. That's supposed to be a 2. That's supposed to be a 3. And does anyone recall what the inverse sign of 1/2 is? Let's do it in radians, because that's usually what they use in calculus. Inverse sign of 1/2. Anyone remember? Pi 6. Okay. And then again, the 2 here will go into 6 here 3 times. So this gives you an answer of pi ninths. Which will be a number fairly close to 1/3. A little bit more than 1/3, but fairly close to it. Oops. Whoops. Messed something up here. Okay, now they did something rather bizarre here. But evidently theirs is right and mine's wrong, but I'm trying to figure out why that is the case here. They just had the pi 6, which we had here, without the 2/3 in front. And what they did, I think it was when I was doing from memory, and I must have botched something up when I did that. 3x minus x squared was 9/4. That's all under radical. 9/4 minus x. Okay. Oh, sorry about that. I divided by this, and this never was divided. In the sine function, you don't do it. In the secant function and tangent function, you do. It's not here. I'm sorry. That was never there. Should never have been there. It wasn't there here either. And it wasn't there here either. So that's why it turned out being pi 6, not pi ninths. Okay, sorry about that. I flipped back and looked at the wrong thing. The 1 over a doesn't show up in sine, it does over tangent, secant. Sorry about that. But that was example 5, pi 6, which whatever that turns out to be. So, finally through with that one, and we've got just a few minutes to go, so let's hit this while we can. Back to current slide. Okay, review of the basic integration rules. You now have completed the introduction of the basic integration rules. To be efficient at applying these rules, you should have practiced enough so that each rule is committed to memory. Not, okay, again, I hate memorizing. Use them frequently enough. That's what they're saying. Practice enough, use them frequently enough so that they get to be like your first cousin. You don't have to sit down and memorize the name of your first cousin if you're anywhere close to them. You have lived with them all your life. You live with these long enough, you can do it. First, if you have an integral of a constant times a function, pull the constant on the outside and it's just the constant times the integral of the function du. Okay, that's pretty simple. Other, it's the constant multiple rule. This is the sum or difference formula. The integral of a sum or a difference of two integrable functions would be the sum and the difference of their integrals. Okay, that's pretty straightforward. If you just have a du, an integral undoes the differential. That leaves you u plus c. That's fundamental theorem of calculus part 1 or first part or whatever you want to call it. Power rule, integral of u to the n, du is going to be u to the n plus 1 over n plus 1, plus some number c. Always a plus c here. Integral of du over u is not a power rule, that's the log. Log of absolute value of u plus c. Integral, my favorite of all time, of e to the u du is e to the u plus c. Okay, that's easiest to integrate, easiest to differentiate. But if it's some other base other than e, a to the u du, then it's a 1 over log a times, just like we did here, a to the u plus c. Okay? Number 8, the antiderivative of sine is minus cosine. Antiderivative of cosine is positive sine. Antiderivative of tangent is minus log absolute value of cosine u or log of absolute value of secant u. Either one of those is acceptable. Plus c. Integral of cotangent, very similar to what you had here, only you lose the minus sign and it's just log of sine. So therefore these look different if you put the cosecant, put secant in here because it's 1 over cosine, but they still, I think that's the easier form to deal with. Antiderivative of secant u is that strange one, log of absolute value secant u plus tangent u plus c. That trick. Cosecant u, similar to this, same trick, minus the log of cosecant u plus cotangent u plus c. Antiderivative of secant squared is tangent. Cosecant squared is minus cotangent. Antiderivative of secant tangent is secant, and antiderivative of cosecant cotangent is minus cosecant. Alright. And then the inverse trigonomes, if you have a form like this, that's the square root of an a squared minus u squared in the denominator, that's an inverse sine. No coefficient, like I blew last time, of u over a. Square root of this one over the square root of that one. Okay? Plus c. If, however, you have the sum of two perfect squares in the denominator, one being a constant, one being a variable, any kind of a variable, it's 1 over the constant. There you do put the 1 over a constant. Arctangent of u over that constant. The square root of this u squared. That's plus c. And if you have the integral, of the du over u times the square root of u squared minus a squared. This is your arcsecant. Again, with the 1 over a in front and the absolute value of u over a here, plus c. Alright, those to me are not worth memorizing. I'll look those up in the table. These two I use often enough to know this one, and that one. This one I'm always going to look up just to make sure I don't have a sign wrong or something like that. All right, example 6, top of page 369. How are we doing on time? 10 minutes or 9 minutes. Find as many of the following integrals as you can using the formulas and techniques you have studied so far in the text. Okay? Anyone want to make a guess of what this looks like? I thought someone would answer. If not, I've got to go to the white page. All right, go to the white page. Y'all just want to make me suffer, don't you? Okay, let me clear this out of the way. Okay. That was integral of dx that's a d, it's ugly d, but it's a d, dx over x times the square root of x squared minus 1. Okay, folks, that is classic form of secant absolute value x. Plus c. That's it. I mean, that's all there is to it. I'm sorry. Inverse. I keep forgetting to write my minus 1. Inverse secant of absolute value of x dx plus c. Okay? The next one, this is one similar to one we just did not long ago. Here we have x dx over square root of x squared minus 1. Okay. Now this isn't one you just jot down. This one you have to work just a little bit on. It's not a hard one, but you just have to do a little bit of work. What would be your first step? Anybody? When in doubt, substitute. If your players aren't producing, substitute. No, okay. And what would you substitute? The innermost part of your most complicated part. That would be your x squared minus 1. Let u equal, I've left off the u here. U equal x squared minus 1. Then always follow the let by then. Du, and that's how it usually begins, is equal to, derivative of this is 2x minus 0, because derivative of a constant is 0. And that has a dx with it, because the d's always have d's. Okay, we don't have an 2x dx, we just have x dx, so we divide out a 2. Alright, here the 2's cancel out. Goodness gracious. Okay, so with our u substitution, this becomes a 1 over 2 times the integral of, and the x dx is du over 2. We already got the over 2, so this is just a du. And this is u to the 1/2 power down here. We did one almost exactly like this before. Well, that's a power. That's a 1/2 the integral of u to the minus 1/2 du. Whoa, I'm getting tired. I can't get the fingers to work well. Okay. Oh, goodness gracious. And what would this be? Gonna leave the 1/2. Well, I'll write it in. I know what's gonna happen to it, but let's just go. That's gonna be a u. Up that by 1. That would be to a 1/2. And multiply that by, or divide that by 1/2, which is the same as multiplying by 2. And then these two go out. And this will be, oh no, no limits. So that will just be a plus c. U to the 1/2 plus c. And what's u? Almost forgot we had a substitution there. That would be the square root of x squared minus 1. Plus c. Be sure you have that plus c outside the square root. Square root of x squared minus 1 plus c. Okay. Do we have time? Yeah, let's try it. The c one. Okay. All right. C is the integral of dx over the square root of x squared minus 1. All right, that looks awfully close to being an inverse secant, but it's not. The inverse secant has an x in front. Okay, you cannot find the integral using techniques that we've studied so far. You can look over the basic integration rules. What you can also do is go back and do it sort of the way I was doing before. That is a 2 there. I thought it looked like a 9. Not going to be able to do that. So I'm afraid we are almost out of time. That one's not doable from what we have so far. We have example 7 to go. And I think that is the last example before section 5.8. Okay, I mean the exercises. Let me give you the homework exercises here. Any of the odds 3 through 21, they're all at Calc Chat. 5's at Calc View. 23 to 33, they're all at Calc Chat. 33's at Calc View. 35 to 41, all at Calc Chat. 35's at Calc View. 43 or 45, they're both at Calc Chat. 45's at Calc View. 47 or 49, both at Calc Chat. 47's at Calc View. 51 or 53 are exploring concepts. You can look at those if you want to, do them if you want to. Should be at Calc Chat. You can do 55 if you want to. That should be at Calc Chat. 57 or 59 should both be at Calc Chat. 61 should be at Calc Chat. 63 and or 65 are at Calc Chat. 63 is at Calc View. 67 is at Calc Chat, as is 69. So either 67 or 69. 71 is a true false. This should be at Calc Chat. Either 73 or 75 should both be at Calc Chat. 77 is a numerical integration. We haven't done anything directly like that except before. I mean, earlier when we were first introducing that, you might be able to tackle that one. And then there's some further information on page 370, bottom of 372, if you see something for a paper topic. The rest, 5.9, is hyperbolic functions. I'm not going to do this. Do any of you have any idea if your major uses hyperbolic functions? I don't hear anything. I would say just look at the hyperbolic I don't know. I found them more complicated. The definition of hyperbolic functions you'll see at the bottom of page 373 shows that every one can be done in terms of exponentials. And to me, exponentials are so much easier to work with than hyperbolics. I don't know why they even introduced hyperbolics. So work with the exponentials. That's what I do. And if you ever need to do it, look it up in a table. So we're going to skip that, and certainly inverse hyperbolics. Um, and so you don't have any homework exercises there. There are review exercises at the end. Well, I'll talk about those next time. And I have your test ready now, but I will post it right after class on Wednesday, so you can start working on that. Do some of you want to go on and get started now? I'll post it sometime. Okay, so what I'll do is I'll post it. I've got a class starting in 3 minutes, so I won't be able to do it now, but sometime after 6:30. Did I post it already? I don't think I did. I'll post it next sometime this evening. Okay. Any last thoughts? Parting shots? Yeah, 5.9 you don't have anything to do in that because that's the hyperbolics. 5.8, um, didn't we? Did we start in 5.7 today? Yeah, we started in 5.7, so you have that. But once you get your tests, don't worry about homework anymore. Focus on the test. Unless there's something you can't figure out on the test and the homework would help you and you can't figure it out there, send it to me and I'll try to help figure out where you're going wrong if you're not getting the right answers. Okay? Alrighty. Okay. I've got another class coming up in 2 minutes now, so I'm going to have to say goodbye today. I'll try to get the test posted before end of the class today. Before the end of the day today. All right. Any last thoughts? Parting shots? Okay. Going to end recording then. Catch you later on Wednesday. Okay, I've got Don Baldwin here, I believe, and Nakia Caldwell. Conwell, I'm sorry, I mispronounced both of your names. Okay, Cormisha's coming in. Okay. Roy is coming in. Jacob is coming in. Howdy, that's Roy, right? Okay, good to have you. Still got people coming in slowly here. Say that again.
Looks like somebody has an actual microphone.
Oh, yes. My wife got it for me last week and we tested it over the weekend and it worked. So this way I can turn my heads and y'all can still hear me, okay? So finally moving up to where we should have been probably all along. While we're waiting for someone else, I'm going to try to get my PowerPoints open because I just finished the last class. They had questions at the end. I only had 5 minutes and there just wasn't time to do everything. So let me get this done. We're wrapping up chapter 17 today, and we'll probably move into 18. I tried to open 2 chapters in the last class. Goodness gracious. Okay. And the first one, they both were open for the first several times, and when I finally finished the first one, opened the second one, it had disappeared. So I don't know where it went. So that may happen to us today too, but we're going to try it otherwise. Okay. So let me get back to Zoom. Okay. David's waiting. Let me get him in. Okay. Let's see what we've got so far. Who we've got so far. Should have 6. 1, 2, 3, 4, 5, 6. Yep. My last class started awfully small. In fact, it didn't even finish too big either. We had a lot of absences. Okay. And this class is not starting to. Oh, here's 2 more people. Let me see who they are. Oh, David's joining twice. Okay. I let him in once, and now he's joining twice. So we're still at 6. I thought we were adding 2 more, and it was David twice. Okay. Well, David, are you in here at least once?
Yes, sir.
Okay, good. Your name showing up is still waiting, and yet you're showing up as here too. So I don't, I don't know either. And for some reason, I've got a group chat that's trying to do something, and I don't want it to. So I'm trying to. Okay, here we go. All right. Yeah, I see you in here now. It was blocking me. 1, 2, 3, 4, 5, 6. So still only 6 people. Don't know where everybody else is. Any questions, issues, concerns that need to be addressed? All right. If not, let's go on and let me start a screen share on. We've already done that. Okay, let me try that again. Screen share on chapter 17. And here it did it. Oh, there it is. There we go. All right. All right. While I was doing that, did anyone else try to get in? Let me move this down out of the way. Let's go from current slide. Oh, you know what I forgot to do?